In this paper, we describe the measurements of apatite grains from several lunar highland samples for their water content and hydrogen isotopic composition. Up until now, very little attention has been paid to the volatile inventories of samples of the lunar crust, which is surprising since they represent some of the oldest samples we have from the Moon. This slide shows some of the apatite grains from the 4 Apollo lunar samples investigated in this study, shown here in backscatter electron images. We have the granite-classed 14303, troctolite 76535, and 2 norites 77215 and 78235. These samples represent rocks belonging to the magnesian and alkali suites, and collectively span an age ranging from 4.31 to 4.44 billion years old. All of these samples contain apatite, which is a calcium phosphate mineral, which can incorporate variable amounts of volatiles in its crystal structure. Apatite is the most commonly occurring hydrous mineral in lunar samples, and is thus really important for our investigations. In this study, we used a Kamika nanosecondary ion mass spectrometer, a NanoSIMS, to measure the hydroxyl content and hydrogen isotopic composition, expressed in a delta notation, of the apatites in these samples. This secondary electron image shows examples of the sputter pits created by the NanoSIMS. For lunar highland samples, which have been exposed to the lunar surface environment for some time, it is important to take into account the effects of cosmic ray spallation reactions, as exposure of samples to this spallation process can alter their original D/H ratio. We have corrected all of our raw data to take this effect into account. In the case of troctolite sample 76535, the apatites were very dry, such that the hydroxyl couldn't be reasonably resolved from our analytical background. In addition, applying the correction for spallogenic hydrogen and deuterium was quite tricky, and so the results of this sample have been omitted from this summary. Of the other samples, the 2 norites and the granite class, the final results are presented here. Prior to this study, only 2 data points for apatite in lunar highland samples were reported in the peer-reviewed literature by Greenwood et al. 2011. Here we have plotted their data for comparative purposes. Notice the general spread in hydroxyl content, up to almost 4,000 parts per million, which is the highest so far recorded for apatite in lunar highland samples. Notice too the consistency in delta D values, especially for norite 77215. By adding some contextual information, we see that the results of this study show that apatite in lunar highland samples tend to have lower delta D values relative to apatite in lunar basaltic samples. In contrast to the highland samples, the delta D OH systematics of apatites in the basalts are thought to have been affected by hydrogen degassing from the parental melt, resulting in relatively elevated delta D values due to fractionation of hydrogen from deuterium. The apatites analysed in this study seem to suggest that degassing did not play a significant role in affecting the delta D OH systematics of apatite, and thus they may reflect their true indigenous values. In terms of solar system source regions, the delta Ds are comparable to those of some carbonaceous chondrites and estimates of Earth's mantle. In light of these results, and given that the 2 norites and the granite-classed are coarse-grained, likely plutonic rocks, which are thought to have crystallized at depth in the lunar crust, we can suggest that the apatites have largely retained their original delta D OH systematics. It is interesting that these apatites contain appreciable amounts of water, indicating that their melts from which they grew were hydrated to some degree. Thus we can infer that the magmas involved in secondary cross-production on the Moon were hydrated, which agrees with the recent findings of Hui et al. 2013. The fact that the highlands apatites show such comparable hydrogen isotopic signatures to those of some carbonaceous chondrites and the Earth suggests that there may be a common link between water in the Earth-Moon system. Whether this water was accreted with moon-forming material, essentially derived from the proto-Earth, or whether water was accreted to the Earth-Moon system shortly after moon accretion, remains to be resolved. In summary, this study has demonstrated that analyses of apatite grains from 3 ancient lunar highland samples suggest that the melts involved in the formation of the lunar crust were hydrated. Our results also strengthen the hypothesis for a common origin of water in the Earth-Moon system.